On slide 13, we take a first step towards trying to answer the question what's missing in regular latent transition analysis. First of all, we recognize that we're talking about longitudinal data analysis. Second, we can view the data also as nested or hierarchical data, where we have time nested within subject. In the latent transition analysis model, we have U being influenced by or predicted by the latent variable C. We're going to make it a little bit easier by, instead of C, we're going to consider a unobserved covariate X influencing the binary U variable. So let's take a look at a two-level model formulation for this, where level 1 is time and level 2 is subject. So on level 1 we have the usual logistic regression expression that we discussed in a previous segment. So we have a dependent variable which is the logit or the log odds for the probability of U, and we write that in the form of an intercept and a slope times X part. Now the interesting thing is that the intercept is random, has a subscript J, so it varies across subjects. And on level 2 then we can write that variation across subjects in terms of a beta 0, which can be seen as the intercept mean, but we also have variation, a residual, which is then saying that certain subjects have a higher or a lower value than the mean. And the variance for that residual is a parameter sigma squared U. So Uj, that's a description of the dependent variable level, irrespective of the influence from X. Now in terms of a model figure, we can describe that in this way, in a two-level long format. You have a U regressed on an X, logistic regression with slope beta, and we have a random intercept which we denote by a filled circle here on the time level, and it becomes an open circle, a continuous latent variable on the between subject level. So you have the parameter beta, and you have parameter the mean beta 0 and variance sigma square U, 3 parameters up here. Certainly if you do two-level modeling, you would never dream of at least having the intercept being random. You wouldn't want to have that to be fixed and the same for all subjects. You could also have the slope being random, but typically the most important piece to make random is the intercept. Now we can write this two-level model in a single-level format in a quite equivalent way as we have shown here on the right. So here you have 3 time points. U is measured at 3 time points, influenced by X at the 3 different time points, different values of X at the 3 different time points, with slope beta, which is in common for all time points. Beta does not have a subscript T here. And then U, the random intercept, influences the U variables directly with fixed coefficient 1, corresponding to the invisible 1 multiplying U sub j here, so that it's the same, it's not varying across. The influence of Uj is not different for the different time points T here. Once again, you have 3 parameters, beta, mean of this, beta 0, and variance of this. Alternatively, you can have the mean of the random intercept being 0 and put that level related parameter here instead as thresholds, for instance. Thresholds then are held equal across time. So if you analyze data here, you can arrange it in long format or wide format, and if you do maximum likelihood estimation, you're going to get exactly the same log likelihood value and exactly the same parameter estimates. So it's an equivalent formulation of the same situation. Now on slide 14 we make a little bit of an aside talking about panel data, particularly in econometrics, where we have a interesting idea of being able to deal with time invariant omitted variables. If you look at this equation here, once again, u sub j intercept, and then we write out the intercept beta sub j plus epsilon j, and then we have a beta x term. Why that random intercept part, that is, why that residual is so important, is because if you have left out, not measured some variable z, a time invariant subject varying variable, whatever it might be, a continuous variable here, it can be picked up by a random effect here so that the estimation of beta doesn't get distorted. So that's the positive part. Now econometricians have criticized the random effect approach to this by saying that it's likely that this u variable, u sub j here, is correlated with x. That is, you should really include a correlation like this. This is how the model should look. Because the u sub j, as we said, it's a function, it represents rather the level of the dependent variable, higher or lower. And that dependent variable phenomenon or characteristic is likely to be correlated with the between level part of the x variables. The between level parts of the x variables are likely to be correlated with this between level part of the y variable. So these correlations. And that's true, but that's not a problem for us if we do this multi-level modeling correctly. So for instance, if you have this logistic regression equation in two parts, level 1, level 2, you can group mean center the x's by subtracting the group mean from each x observation, and on level 2 you can add the group mean variable. In fact, it's sufficient to avoid this problem, it's sufficient to include this group mean variable and keeping the x variable as it is, the whole full x variable here, because once we have included the x bar here for uj, the residual delta j will be likely to be uncorrelated with the full x, because the group mean has been included here. That's the Munlach formulation. I can give you references on that later on. So the critique is not really a problem for us, and in fact we're not going to work with time varying covariates here in the models that we're going to take a look at. But you should keep in mind that if you do, you want to take a look at this formulation, which is then described in Wright and Bush and Breich. Table 5.11, for instance, discusses exactly this beta sub w and beta sub b, the within level beta and the between level beta, and the difference between them is the contextual effect. Anyway, this is a good model to separate within level phenomena from between level phenomena. Now you can do even better than centering with x bar j, the observed sample mean. You can use latent variable centering, and my colleague Tihomir Asparhov and I have written a paper that appeared recently in the journal Structural Equation Modeling. Now when it comes to this fixed versus random effects literature, which you should be aware of so you're ready to answer any critique, you have econometric sources like Wooldridge, Econometric Analysis. He also has an econometric textbook covering this. Paul Allison has done some nice work on this in several papers, trying to convince econometric researchers that you can handle random effects modeling just fine, and it actually is better than fixed effects procedures. Boland and Brandt had a paper here describing structural equation modeling, how this can be done in a general fashion within the SEM framework. A very nice article in Political Science Research and Methods by Bell and Jones talking about this same matter, very clearly laid out. And Bu and Satora has a nice application with business examples in organizational research methods, and John Antonakis has a nice recent overview as well of this in organizational research methods. And then Ellen Hammaker and I have a paper that's coming out in Psychological Methods, where we describe the connection to multi-level modeling to try to clarify this issue further. Now, on slide 16, going back to then the single indicator LTA, that is the hidden Markov model here, we have learned then that what it really should look like is like on the right, adding a random intercept influencing all time points, a time invariant effect, a time invariant variable. And that has not been very much used, however, in hidden Markov modeling. Probably because the hidden Markov model on the left can use the fast backward-forward or forward-backward so-called Baum-Welch algorithm for ML estimation. Because you have the simplifying feature of the U's being uncorrelated, independent, conditional on the C's. The U's are only connected via their connection to the C's. And when you look at this model on the right, you lose that simplicity. The U's are no longer independent, conditional on the C's, because they are still correlated with help of the U variable. This means that if you consider maximum likelihood estimation, it's going to need numerical integration with respect to a single dimension U, which leads to much heavier computations in this mixture setting that characterizes latent class and latent transition analysis. It's a mixture of different classes. If you want to read about estimation matters, there is a 2012 book by Bartolucci and others, Latent Markov Models for Longitudinal Data. There is, however, an application of this random intercept hidden Markov modeling on slide 17 by Altman in JASA, Journal of the American Statistical Association. And she considered relapsing remitting multiple sclerosis patients, a sample of 39 subjects, where symptoms worsen and then improve in alternating periods of relapse and remission. So the outcome here is a number of lesions in the brain. It's a count variable, which makes the computations even more difficult. The number of time points, T, is 24, monthly scans for 2 years. And you consider two latent classes, these hidden states of relapse versus remission. It's an impressive work, particularly since unlike other maximum likelihood estimation, this is not with mixture models. This is not done by the EM algorithm, but actually observed data log likelihood optimization. I think it was her dissertation, actually.